Okay, good afternoon. I'm Steve Chartel, Dean of our School of Public Health here at Berkeley, and I want to welcome you to this symposium or panel discussion on swine flu, H1N1, or whatever we choose to call it as this evolves. I also want to call your attention on the screen to a major symposium we're having this Friday on campus, also sponsored by the Berkeley Alliance for Global Health, which is a compendium or a consortium of two campus research centers, our Center for Emerging and Neglected Diseases and our Center for Global Public Health. That symposium will be at the Alumni House this Friday from 9 to 3, and it's going to address global change on a big scale, looking really at the interactions among climate change, population growth and migration issues, and also technology, new technology developments and so forth, as those kinds of forces interact. So that may be of great interest to many of you as well. Today's topic, again, is on swine flu, and before we begin and I introduce our panelists, I really want to thank 3 or 4 people here for pulling this together on such short notice. And that includes Tamina Madan and Miriam Rafiq from our 2 centers. And also I want to acknowledge Sarah Yang from our Public Affairs Office and some of the media coverage here so we can get the word out to the larger public, and also the Provost's Office for publicizing this event. And thank all of you for joining us. It's also a great example, I think, for those of us who are here at Berkeley of what we pride ourselves on, the integration of discovery learning and service learning. The discovery in terms of the research that goes on to try to find vaccines that can prevent some of these infectious diseases, as well as research on new forms of surveillance systems and early warning systems. You're going to hear that from the panelists, but also then in terms of service learning, as our students interact and our faculty interact to get this information out to the public to be better prepared. So without further ado, let me introduce our panelists today. Our first panelist will be Art Reingold. Art is the Edward E. Penhote Distinguished Professor of Global Health and Infectious Diseases in the School of Public Health. He also serves our Associate Dean for Research and also heads up our Division of Epidemiology. And he doesn't sleep, he's not allowed to. Art studies the epidemiology of emerging and infectious diseases, the effectiveness of available vaccines and drugs. He's going to discuss some of the transmission issues, the surveillance issues, the prevention and containment strategies, and also the also some of the international responses that are going on. He will be followed by Russell Vance. Russ is an assistant professor in our Division of Molecular and Cell Biology on campus, and he explores the fundamental biological processes underlying infectious diseases and the immune system's response. He's going to discuss the influenza pathogenesis, the human defenses, and how the virus rapidly mutates to avoid extermination. Our third panelist will be Wayne Getz. And Wayne is professor in environmental science, policy, and management in our College of Natural Resources. And he studies the ecology and epidemiology of wildlife and human diseases in developing country settings. He's going to discuss the complex ecosystems and environmental factors that influence the spread of these diseases in many parts of the world. And batting cleanup today is Professor Amy Herr, assistant professor in bioengineering in our College of Engineering. And Amy's designed a very innovative lab-on-a-chip diagnostics that can be used to detect pathogens in the field. And she's going to discuss the value of this point-of-use technology in preventing pandemic-prone infectious diseases, as well as the challenge in adapting these diagnostics for use in poor settings. So we're going to start with Art Reingold. Art.
Somebody needs to help me with this computer. Where's the cursor here? Where's the cursor? All right. No. Okay. Sorry. Great. Okay. Thanks. Good afternoon. Thanks. So what Steve didn't say is our plan is for each of us to talk for no more than about 10 minutes and then leave at least about 30 or 40 minutes for questions and discussion, because I suspect that there are people who have questions. So this is meant to be partly presenting facts, but largely an opportunity for you to ask questions. And we may even have an answer or two. So this slide simply summarizes on one slide some of the basic facts of influenza viruses. As many of you know, they come in three flavors, A, B, and C. Influenza C virus is not really an important human pathogen. The illness it causes is very mild, and we don't really worry about it. Influenza A and B viruses, on the other hand, are important causes of morbidity and mortality. And just as for a guesstimate, each year about 35 to 50,000 Americans die of seasonal influenza, which is typically a mix of influenza A and influenza B. These viruses have 16, as Russell will probably go over in more detail, 16 hemagglutinins and 9 neuraminidase, which give rise to this somewhat daunting nomenclature in which we talk about whether it comes from a human or an animal. We say whether it's an A, a B, or a C strain, and then we talk about where the strain was first found. So an H3N2, an H9N2, et cetera, is how we keep track of these viruses. And as Russell will also talk about in more detail, they are genetically very mutable. They're able to swap genetic information, and they undergo very, very rapid evolution and change in terms of their antigens and their other properties. The incubation period for influenza, and as far as we know for the swine flu, which I'll be talking about more specifically in a minute, is typically in the range of about 2 days with a range of 1 to 4 days. And what's most important to point out about this virus and about influenza here is the fact that unlike a disease like SARS, people with influenza begin to shed the virus. It's detectable in their nose and throat the day they become ill. In fact, it's actually detectable in the nose and throat the day before people develop symptoms. But of course, they're typically not infectious to others until they begin coughing and sneezing. But the virus is present very, very early, and what that means is that people may still be walking around, even though they are at that point infectious to others. A lot of interesting issues to talk about here, which I won't get into in terms of the routes of transmission. If you read the complicated literature on this, you'll see some people saying it's mostly by large droplets, which means that if I cough on Dean Shortell right here, I'll be able to infect him, but I won't be able to reach people in the back of the room because my large droplets will fall to the ground if they don't fall on the Dean. It's pretty clear, in fact, that smaller particles, what we refer to as aerosols, almost certainly can transmit influenza. And then what I would personally characterize as a lot of interesting discussion about whether there's much transmission on hands and on fomites, inanimate objects in the environment. But certainly the basis for the recommendation about hand washing is the suspicion that there might be some transmission possible via this route. But I think most of what we know says that most transmission of influenza is through the airborne route, and if transmission on surfaces and hands is probably a very minor part of influenza transmission. Now, I simply want to point out that when we think about a pandemic of influenza, there have to be three characteristics of a virus for us to get a pandemic. The first is that the virus has to be capable of causing disease in people. The second is that the virus has to be readily transmissible from one person to another. And the third is that the population has to be susceptible to the virus. So in other words, most of us need to be lacking antibody to that virus. And as we'll talk about in a minute, for the bird flu virus we were concerned about up until a couple weeks ago, that virus has met two of those three criteria. The bird flu virus causes severe disease in people, and none of us has immunity to that virus. But the good news about that virus is it has not yet figured out a way to be readily transmissible from one person to another. This just simply gives you some perspective on prior influenza pandemics. The stuff in the 19th century is pretty much guessing. But of course, the three pandemics in the 20th century are very well characterized. And most people particularly look to the 1918 pandemic as sort of, if you will, the worst case scenario, because during that pandemic, the estimates are potentially at least 40 to 50 and perhaps as many as 100 million people died as a result of that pandemic. And that pandemic, we now know through some elegant detective work on the part of virologists, digging up bodies from the permafrost and sequencing the RNA, that was an H1N1 virus as well. And then the more recent pandemics of smaller dimensions were caused by an H2N2 and an H3N2 virus. And this just gives you a sense. These are the kind of data epidemiologists like. So these are death rates per 100,000 for various infectious diseases from 1900 to 1963. And you can see, as you all know, that death rates from most infectious diseases have been trending downward for the last 100 years, largely not related to what medicine or public health has to offer. But you can see in 1918, 1919, this enormous spike in death rates because of the 1918 pandemic. So we're talking about, in that instance, a very, very serious pandemic with enormous morbidity and mortality. And what's striking about that 1918 pandemic, unlike seasonal influenza, where most of the deaths occur in kids under the age of 1 or 2, and in old people like me, is that a lot of the deaths in 1918 were in people in their teens, 20s, and 30s. A phenomenon that has several plausible explanations, but which we really don't fully understand, and I'd be happy to talk about that later if you want. But again, the concern would be, if we have another pandemic, might we see something comparable with a lot of the more severe illness and death occurring in previously healthy people in the prime of life, so to speak. And so if you make projections from the 1918 pandemic for what might happen with a similar pandemic now, the projections for the United States from a 1918 pandemic was that we could potentially have 90 million cases, 4 million outpatient visits, 10 million hospitalizations, 2 million deaths, and healthcare costs of over $250 billion. And that doesn't count in the economic loss and harm, if you will. So when people think about a huge pandemic, they're absolutely talking about a very, very substantial public health problem. And up until 2 weeks ago, when people were thinking about that, they were mostly focused on the H5N1 virus, the bird flu virus, which this simply shows, as you can tell here, the dark yellow are countries where the virus is present in poultry and wild birds. The light color countries are where it's present only in wild birds, and the red are the human cases. And so as of basically a couple of weeks ago, this virus had managed to infect about 400 people around the world, for fatality about 60%. So a very, very serious illness caused by that virus. But that virus, fundamentally, all of those infections, or almost all of them, were caused by bird-to-human transmission. And that virus, again, has not figured out how to be readily transmissible from one person to another. But this was the virus that had many people thinking about pandemic influenza and planning for pandemic influenza, and was basically the virus people were worried about up until about a week and a half ago, when the outbreak appeared in Mexico. Whether it originated in Mexico, we could probably talk about, but where it at least appeared in Mexico. So what do we know? Well, as of today, I guess, we know that this virus, this H1N1 virus, is widely present and has been confirmed in many states, including here in California and in the Bay Area. It's also managed to make it to a number of other countries around the world, and that basically all of this, in virtually all of these cases, at least initially, represents people getting on airplanes and traveling from Mexico either back to their country of origin or to one of these locales. Although there certainly has then been subsequent transmission within the United States to people who never set foot in Mexico. So there is certainly ongoing person-to-person transmission, but most of these cases, at least initially, represent people who were infected when they were in Mexico. And I can't see this very well, but this just shows the cases mapped out here. This is from this morning's website. So what do we know about this influenza so far? Well, so far, clinically, its features are indistinguishable from annual epidemics of influenza. So clinically, it's no different. Currently, the virus that's causing this problem is susceptible to Tamiflu and antivirals that might be used for this disease. As Russell perhaps will talk about, the virus appears to have genetic elements from 2 different previous H1N1 strains. An interesting question about how they managed to get into the same virus and into people in Mexico. At the moment, the best guess is that all of us who've had annual flu vaccines are not protected against this strain, even though the annual influenza vaccine does contain an H1N1 virus. There's very little similarity between what's in the vaccine and this virus causing the problem at the moment. So we would have to assume, until there's more research done, that none of us is protected against this new strain. We do not have a vaccine against this strain, and we can talk about how we might get one. And the other thing to point out is it's certainly going to be the fall until we have even a modest number of doses of a vaccine for reasons I'll get to in a second. What don't we know about this virus? Well, that's a much longer list, and I'll only give you a few examples of things we don't know. If we assume that transmission will decline at the end of the flu season here, which we're now at the end of, that's an assumption, but it probably is a correct assumption. But will the virus cause widespread disease in the southern hemisphere, whose flu season will be beginning soon, because their flu season is in the winter in the southern hemisphere? So we have no idea what to expect in the southern hemisphere. And perhaps also of great importance, we don't know if the virus will reappear here in our next flu season. We don't exactly know where flu viruses go between flu seasons, whether they hide out in a different part of the globe or whether they have some strategy for remaining undetectable in people. But it's pretty clear that viruses present at the end of one season can reappear the next season. And that's one of the major concerns. Will the virus reappear next winter? And if it does, will it become more virulent, less virulent, or stay the same? And of course, the related question is, will we need a vaccine against this strain? And if we have one, will we in fact use it? So just to finish up, this is from looking at H5N1, the bird flu vaccine, but this basically points out, based on current capacity worldwide, in terms of a base or most likely case in 2009, how many months it would take to meet global demand if one wanted to vaccinate everybody in the world, and if everyone needed 2 doses of vaccine. And you can see with current global capacity, that would take about 4 years to produce enough vaccine to vaccinate the entire world. So when people talk about having vaccine ready for the fall, they're talking about limited numbers of doses and certainly not enough to vaccinate the world's population. And let me just, in closing, point out one of the conundrums we have, and this dates back to the last time swine flu was a problem, when we had a small cluster in Fort Dix, New Jersey in 1976. Actually, there were also cases of H3N2, but there were confirmed cases of H1N1, including a death in an 18-year-old who went on a prolonged march while ill. There was no evidence at the time in February of that year that there were swine flu cases in nearby civilian populations, but basically a decision was made in February to do 2 things. One, to make a vaccine against swine flu, and also to use the vaccine. And so what happened was work proceeded to make the vaccine, and despite the fact by October that there was no obvious continuation of the epidemic, the decision was made to go ahead and use the vaccine. And so what happened was they began mass immunization. About 1 million people vaccinated the first 10 days. On October 11th, 3 elderly people who got vaccinated died abruptly after getting a vaccine in Pittsburgh, leading to a suspension of the program, a loss of confidence, if you will, in the safety of the vaccine. And as a result, in order to reinstill confidence, President Ford went on television and had himself immunized in order to reinstill confidence in the vaccine. So here you can see him cheerfully getting his flu shot, and his family as well. And so basically immunization continued. About 40 million people were ultimately immunized, but the campaign was suspended when vaccinated individuals began to develop a serious neurological sequela called Guillain-Barré syndrome. So this looms in the background, if you will, in terms of making decisions both about whether to make a vaccine, and if we do have a vaccine, under what circumstances would we actually administer it to people. And that will be an interesting discussion in the fall. So let me stop there and turn it over. We're going to wait and take questions and have discussion, I think, after everyone talks. Is that right? Okay. So, Russ.
Okay, I need some help. My name is Russell Vance. I'm an immunologist in the molecular and cell biology department. And thank you, Tamina. So I thought what I would do is just expand a little bit on what Art was telling you already and give you a little bit of background about the biology of the virus. Because actually understanding something about the biology is pretty important for understanding where this virus came from and where it may be going. So this is actually a picture of an influenza virus. And it's basically like a spheroid shape, and it has all these studs protruding from its surface. This is an electron micrograph of what the virus looks like, and then this is kind of a schematic representation showing you the same thing, basically. So it's sort of a circle, sphere, and it has these proteins studding the surface of the virus particle, and we'll come back to those in a second. Really probably the most important part of any virus is its genetic material, its genome, and it's this genetic material that provides a blueprint or the instructions that the virus has to use to replicate itself. Okay, and so I'm showing the genome of the influenza virus here in this diagram in these pink segments. Okay, and there's really two key things about the genome of influenza virus that I think you have to understand if you want to understand how this virus works. And the first point is that the genome is made up of a nucleic acid called RNA, okay? And that actually differs a little bit from our genomes. Our genomes and most living things' genomes are made of DNA, and that's very closely related to RNA, and there's subtle chemical differences, but those make a pretty big difference. And one of the important differences about RNA is that it tends to be mutated very rapidly when it's replicated, okay? So this is an RNA virus, and as a result, one of its characteristics is that every time it's replicated, it is not perfectly replicated. There are errors that are made. These are called mutations, and eventually these accumulate, okay? So basically, influenza virus is replicating all the time, and that means it's changing all the time, okay? So this is not a constant thing. And the typical change that we see every year with the influenza virus, we call it drift. Okay, and this drift, or this change that occurs to the virus over time, is why we need to get new vaccines every year, okay? Because the old vaccines recognize the old virus, but the virus drifts, and so we need to come up with a new vaccine every year in order to protect us against the new strains that emerge, okay? So this happens every year. This drift is a very normal part of what happens with flu, okay? Now the other thing that's important, the other important feature of the genome of the influenza virus is that it's segmented, okay? As you can see here, there's 8 segments, separate pieces of RNA, if you will. And each piece encodes for 1 or 2 different protein products, okay? And so for example, here I have the HA segment of the genome, and this encodes for a protein which ends up on the surface of the virus particle called hemagglutinin. And then there's NA, which encodes for this protein here, neuraminidase. Okay, and so these H and N proteins are on the surface of the virus particle, and they're really probably some of the more important proteins on the virus particle. And they're used basically by the virus to get in and out of cells, okay, in and out of our host cells. So when it infects us, it uses these proteins to get in and out of our cells. And right, so basically all of these, and then there's other segments which encode for other proteins which are important for the virus, okay? But the key point is that the genome is segmented, okay? And what this means is that viruses can swap segments with one another, okay? So if 2 different viruses infect the same cell, they can swap around their segments, and then what can emerge is a new reassortment. Okay? And so this is another mechanism that influenza viruses can use to really change very rapidly. You can get these novel mixtures being created, and so when these novel reassorted viruses are created, we refer to that as a shift. Okay? So drift happens all the time, and shifts are more rare. There's been only a few examples, so I'll show you the next slide, in human influenza of these shifts occurring. Okay, and I think Art sort of went over this briefly, but it's basically a timeline here. And you can see here's the 1918 flu, which was very serious, obviously. And that was actually caused, as Art said, by an H1N1 virus. And so what that means is that it has a hemagglutinin, which is in the family of hemagglutinins that we refer to as H1. And there's actually 16 different families of hemagglutinins, okay, so this has number 1, and it has neuraminidase 1, and there's 9 different neuraminidases that exist, okay. Those are like broad families, so even within a family like H1, there can be lots of diversity, okay. That's kind of an important point to understand. But anyway, this is one example of an H1N1 virus that caused this major pandemic in 1918, and then actually, this H1N1 virus drifted, and it continued to infect people for many years, okay? So that just shows you that an H1N1 virus can cause a very serious infection like it did in 1918, or it can cause so-called normal influenza, as it did throughout the 1930s, 40s, and 50s, okay? And then in 1957, we have an example of this shift occurring. So somehow, probably it was believed, I think, a bird, an avian flu virus reassorted with a human influenza virus, and what resulted was a dramatic shift. And so now these segments H1 and N1 were exchanged for segments H2 and N2. And when this shift occurred, this was actually a relatively major epidemic of flu that year. And the reason that this was a relatively major epidemic was that over these past, previous, 40 years or so, immunity had built up in the population to viruses that were of the H1N1 type. But there was really not any immunity in the population to this new virus, the H2N2. So when it emerged, it's a new kind of virus, nobody has immunity to it, and so it can spread relatively efficiently through the population, okay? So that's why shifts are dangerous, because there's lack of immunity to this new variant in the population, okay? And then the same thing happened in 1968. In 1977, it's believed that there was actually a laboratory release, an inadvertent laboratory release of H1N1 from this era. And now both of these sort of coexist in the population in general, okay? So we have H1N1 flu currently in the population. And this is something that gets confusing to people, I think, because this new virus, this swine influenza, is also H1N1. But it's actually quite different than the H1N1 that's currently circulating now. So that's why we don't believe that there will probably be very much immunity to the new H1N1, even though they're both H1N1 type viruses, okay? Does that make sense? Now, so this is what happened in humans. I just want to talk just for 1 minute about what's been going on in swine all this time. So pigs get influenza as well, and they've been getting it all along. It's been evolving in parallel, essentially, in pigs. And in fact, just to make sure you understand, this is not a one-way thing. Pigs acquired, it seems, or it's believed that the pigs actually acquired the 1918 flu from us originally, okay? So and then it evolved in pigs in parallel for many years. And actually, for about 80 years, the viruses, the influenza viruses in pigs were relatively stable. They underwent some drift, but they were remarkably similar, actually. And then about 10 years ago, in 1997 or 1998, suddenly the viruses in swine started to undergo more rapid changes. And what seems to have happened is that additional influenza viruses from humans and from birds were introduced into pigs. And pigs are kind of unusual because they can be infected with human influenza viruses and bird influenza viruses, so they're kind of a good mixing ground for all of these viruses. And what resulted actually from all of this mixing, which occurred about 10 years ago, was that new viruses emerged, which we call triple reassortment viruses. So they have, and this is sort of a picture of what one of those might look like. So it has some blue segments, which are derived from actually humans, some green from birds, some pink from that were originally pig viruses, okay? And so, and then after this event occurred, and these mixture viruses, they sort of took over in the swine population. And so now most of the viruses circulating in pigs are actually of this triple reassortment type. And then they started, something seems to have happened at this point that allows the virus to really start changing much more rapidly. And there's a lot more rapid evolution in the viruses that happened the last 10 years. And it really is about 10 years ago, people started getting worried that maybe one of these swine influenza would be able to jump into us. So it was somewhat predicted even 10 years ago that something like this might happen. And so it seems like the current virus that we're worried about is related to these triple reassortment viruses. And this is why there's a lot of confusion out there about, is this a swine virus? Is it a mixture of swine, human, and bird virus? Swine, human, and bird virus. What is it? All of those things are kind of true. I mean, they, in some sense, are distantly related to bird and swine viruses and human viruses from 10 years ago. But really, the viruses that now seem to be, that we're worried about now, this new H1N1, seems to be most related to viruses that were circulating in humans, circulating in pigs in the last little while. Okay, and there's some indication that it might actually be a mixture of a Eurasian swine flu and a North American swine flu, but we can maybe talk about that. Okay, so I think that's, I guess the bottom line is that, flu is a very dynamic virus. It can change a lot of unexpected things can happen, and so we can't really predict where this virus is going, and we can't know for certain if it's going to be, sort of stay mild or become more severe. It's a very dynamic thing, and hopefully you have some sense of that. Okay, so I'll pass it off to Wayne. I don't know, I think Tamina will help.
Oh, okay. Let's see. Okay. And then to keep going forward, I just press this. Okay, great. Thanks. Good afternoon. Before we start, I have a disclaimer. And not being an expert doesn't seem to have stopped Joe Biden from making public statements. So there's no reason why I shouldn't put my foot in my mouth as well. It's a good thing not as many people are listening to us here today. So I was supposed to talk about the ecology of infectious diseases and try and put a perspective on the complexity of the problem, because this is a zoonotic disease that goes from humans to ducks, back to humans, pigs, and so on, as Russell has showed us. But when I started to look through the data, and I am trained from a mathematical perspective, there's some things that really began to worry me quite a bit, and I didn't understand what was going on. So I'm going to talk about that first, and I probably won't have time to get into issues relating to the complexity of diseases and an ecological process. But if anybody wants to ask questions about that later, they can. And I have a few slides on that, so we'll see how much time I have. So one of the things that I asked myself is, what do we need to know now and in the future about influenza? And in particular, not being an expert, I asked myself, what are the sorts of things I want to know now? So the first thing, is this current epidemic unusual in any way? It's certainly getting a very unusual reception from the media and from experts, so it has to be unusual in some way. So what is unusual about it? Well, the first thing that we note is coming late in the season. We don't expect something new to be popping up at this point. So that was a bit of a surprise. The second thing is, and again, Russell has gone over this, is that in some way we've sold this idea of a couple of scary strains. So there's the scary swine flu and the scary avian flu, and the not so scary human flu. But it actually turns out that human flu itself is rather scary, and a large number of people die every year. And swine flu, as I can see it, is not much more scary than normal human flu, but yet we're reacting to it very differently. So what is going on? So one of the things we want to know at this point of time is it unusually infectious? And I don't think this question has been answered. I haven't seen anybody answer it. It may have been answered, but I certainly haven't seen people talking about it. So it seems to be relatively normal as far as that's concerned, except for coming out late in the season. So we have to ask, what is that about? Secondly, is it more virulent than usual? Are more people dying from it? And in Mexico, I guess it does seem to be a little more virulent than we expected, and that came as somewhat of a surprise. And maybe that's part of the reason why we're panicking. But in the US, there have been, to date, as far as I know, the death of one young boy. There haven't been any other deaths. So there's no reason to believe that it's anything other than mild and no worse than any normal strain at this point in time. But I guess people want to remain vigilant because of these other unusual circumstances. And are the mortality rates unusual with respect to age in particular? And one of the signs that we have a big problem, Art showed us this classic W curve, and when young adults start to die of the disease, then we know we're in an unusual situation. In Mexico, again, perhaps more young adults were affected than we expected. Is this rather unusual? How will it pan out? That remains to be seen. But that's another indication on whether we're in a normal flu season or something more unusual. So one of the things I asked myself is, how many people have been dying of the flu and what does that look like? And Art had a couple of graphs up, but this one really struck me. Let's see if I can get this to work. Yeah. So if you have a look, this is after the Spanish or swine flu epidemic of the 1918. This is now 1930 to 1937. If you have a look at all causes of mortality per 100,000 individuals each year, this has been going down somewhat, but only marginally compared to what's happening with this graph over the last century. But if you have a look up here, you'll see that in the 1930s and 40s, lots of people died from flu. More people were dying on average from flu each year than all other causes of mortality. And yet this came down, but it was still relatively high until the 1950s, and you see how low it is here. And even though there were so-called pandemics, in 57 and 68, the number of people dying per 100,000 was way below an average epidemic in the 1940s. So we've actually gotten much better at keeping people alive once they get the flu. Now, I don't know how to explain that because I'm not a medical doctor, but I know that we have all kinds of drugs and hospitals are much better than they used to be, and medicine has made remarkable advances. But if the Spanish influenza were to break out again, that same strain, and we were equally vulnerable to it, would the same number of people be expected to die now as 90 years ago? And to me, the unequivocal answer is absolutely not. I think we're much better now at keeping people alive and making sure they don't die. Now, of course, this is in the developed world, this is in the United States, and we have access to some of the best medical care in the world, along with other developed countries. But if you have a look in the third world where people don't have this kind of access, that's where the real crisis is going to come. So to me, this whole business that's going on in the United States now is a little introspective and maybe a little indulgent, because that's not where the real issues are going to come. If there's going to be a global crisis, it's not people in the US who are going to die, it's people in the developing world who are going to die. And I don't see us talking about this problem at this particular time. Now, I know I was asked to come and inject something a little different, and I do work in the developing world, so I am a little more sensitive to this issue. But I think we don't seem to be paying much attention to where the real crisis will be if there is an outbreak. If there is a pandemic, I don't think too many people will die in the end in the US. But certainly in the developing world, they're going to die en masse. And what are we going to be prepared for that? So yes, it's all well and good that we're preparing at home for the crisis that's going to come. But are we thinking about this as a global issue or only a national issue? So in a normal pandemic, and as I said in the beginning, I think influenza is normally very bad. We expect on average 100 deaths per day during the flu season. That's an average over the year. So during the 2 or 3 months, during the peak of the season, you're going to see 500 or 600 people dying per day. Last year, were we concerned about it? Did we have the media all over it? No, we didn't. So it's really quite remarkable the way we kind of sway back and forth and how things kind of capture the imagination. And as I said, I'm a little perplexed as to why it's captured the imagination to this extent at this time. If you have a look at what people die of at various ages, so we expect that the percent of individuals in a particular age group that die of influenza/pneumonia, so this is not just influenza, but influenza-like diseases, In the age classes from 1 to 4, it's way down the list of causes of death, and 2.5% of all individuals who die in that age class die of influenza. In ages 20 to 29, it's much lower. So when people in their 20s start dying of influenza, then we know something serious is going on. Individuals who are aged 85 and older, the probability that any individual aged 85 or older will live another year is only about 1 in 6. And they're the third most important cause of disease is influenza/pneumonia, and that's at 4.8%. So if you have a look at the disease-induced death rate of influenza, in a normal situation, we can expect 5 to 20% of the population to get influenza each year. This varies and the estimates vary, and to count the number of people who actually got it is difficult because people don't always go to the doctor. But it's going to be somewhere between 5 to 20% each year, and 1 in 1,000 of those individuals will die of influenza, and so we will have 35,000 deaths a year. And so far we've only seen 1 death in a month from swine flu. In Mexico so far we've had 150 fatalities. This number of fatalities, if it were in the US, would have, and we had this death rate, would imply somewhere between 100,000 to 200,000 cases. I don't know how many cases there have been in Mexico. We only know about the reported ones. It hasn't been that many, so this represents a very high fatality rate, and that might be another reason why we're panicking. But we need to understand how many cases there really were in Mexico and what the real fatality rate has been. In the US, there's only been 266 reported cases so far, so this is absolutely a drop in the bucket compared to our normal influenza season. So again, I can't answer this question. I don't know what's going on. So I'm there with Joe Biden. Except Joe Biden is panicking and I'm not. So what about scientific information gathering? As a scientist, it's really important to, as rapidly as possible, before becoming alarmist, to gather the information we need. And the first thing we do is determine the genetic strain, and that we do very rapidly these days, and it's done routinely, and Russell has talked about that. Something that hasn't been spoken about that's very important to mathematical epidemiologists in order to understand the course of an epidemic is something called contact tracing. So contact tracing is who's infected who. So if somebody gets it, we want to know who they got it from, and we want to trace that all the way back to the original case. And in this case, the original case may be a pig or it may not. When an epidemic breaks out, it comes from somewhere. The virus must have been incubating in some form in some place, and it could be a low-level infection in an animal population, or where it goes during the summer season when it's not around in the human population. Maybe it's in some individuals in an asymptomatic form. I don't know the answer to that. But we need the distribution of what's called R0. And so if you look at every individual who gets it, they can give it potentially to a number of other individuals. So if I get it, I might give it to 5 other people before I either get well or die. Somebody else may give it to nobody. Somebody may give it to 30 or 40, and we have this notion of what is called a super spreader. But what's important is to start constructing this distribution. So if 200 people have it at this point in time, can you trace it all back to a single individual? Or was there a first individual who gave it to 3 individuals who then among themselves gave it to 20 other individuals? And what does that distribution look like? This is very important information from an early on into the epidemic, knowing how to predict what's going to happen to the epidemic. It's important to estimate the incubation period, the period of which individuals are infected but not yet infectious. And once they become infectious, how long does it take before they become symptomatic? And I don't know the answer to this in the context of different strains. Is it the same for all influenza strains, or is it different? And if it's different, we better understand that. Because especially the period where you become infectious but you're not yet strongly symptomatic, that's when people go around infecting other people and they're not yet aware that they have a problem. We need to estimate the mortality rates, particularly by age, to know whether it's a very different or normal strain. And we need to estimate recovery rates with and without treatment. Yeah, I think I have to kind of wrap up now, but to me, one of the biggest things is, why is it seasonal? We really don't understand fully the seasonal properties of influenza, and by getting a handle on the seasonal aspects, we'll get to understand the properties of influenza to the point where we have a much better handle on treating and controlling the disease. Thank you.
Okay, good afternoon. Hi, my name is Amy Herr. I'm in the Department of Bioengineering here, and I wanted to step back and give a little bit of a different perspective. As an engineer, my colleagues here at Berkeley and around the country and internationally are working very hard on developing new diagnostic modalities. One thing that we are particularly interested in is developing technology to allow rapid detection of infectious disease. So my disclaimer here is I am not an expert on influenza, absolutely, but I am an expert on development of new diagnostic technologies, and those do include detection of, screening of, and detection of infectious diseases. So today the question we pose is, what new technologies are out there could potentially expedite and enhance our capability to screen populations of people? Some of the populations that were touched upon in some of the previous slides, including those individuals here at home, people crossing borders, and individuals in the developing countries around the world. So I did want to give a little bit of perspective on how this is being done currently, and then I'll just segue. I just have a couple of slides today. Segue into some of the new sort of blue sky, but on the way methods that we're looking at to improve these processes. So right now we're looking at current use of rapid diagnostics for influenza. They absolutely do exist, and they are currently used in clinical settings in the US and in other countries as well. So these are commercially available. There are several manufacturers providing these assays. It is a very fast-growing market sector, and I do venture to say that probably after the current events it will be an even faster-growing market sector. These are routinely used, as I mentioned, not just for diagnosis, but also management of infectious disease. Specifically in this case for patients presenting symptoms compatible with the diagnosis of influenza. So what are the assays and how are they currently run? So the general format for these rapid diagnostics is something that's known as a lateral flow assay, a dipstick type assay. One similar example is a home pregnancy test. Obviously that uses urine, whereas these samples, or these assays use samples that come from the respiratory tract. So we are looking at various respiratory samples here. But again, it is a fairly simple diagnostic to use. A little bit more complex than the home pregnancy test. So the assays, the 15 or 20 that are currently available, are generally done in a clinical setting. Oftentimes, though, they do require some moderately complex clinical capabilities. And I've just highlighted here on the right side of the slide a couple of images of how those assays are done. So there are multiple manual steps that are involved. The assays themselves are capable of classifying the flu as type A or B, as was mentioned before, also the C, but generally not interested in looking at that. The duration of these rapid assays is on the order of 15 minutes to a little bit under an hour. And as I mentioned, they can be done in outpatient or sometimes requiring moderately complex clinical laboratories. So this is just one example of the format. Okay. So we did mention earlier some of the biology of the influenza virus. I just wanted to point out here specifically that these lateral flow, these rapid assays that are currently being used, do look for these nucleoprotein antigens that are inside the virus. I do want to point out that The lateral flow assays that are currently developed may have some detection capability for this novel H1N1 virus, but the performance of these commercially available assays is absolutely not established. So that's something that leads us to sort of an issue with rapid diagnostics for novel infectious diseases. That is, we don't know the sensitivity or specificity, which are the technical terms to basically convey the false positive or false negative rates of our currently available lateral flow diagnostics. For example, if someone came in and was diagnosed as being positive with the lateral flow assay for the A strain, this could basically mean that the person maybe does have the novel H1N1. They could also have just the seasonal A strain virus infection, or it could be a false positive. So there are several different outcomes depending upon the epidemiological situation surrounding the diagnosis with the rapid point of care assay for the influenza. Okay, so the CDC is basically establishing the guidelines that two methods are needed for gold standard identification of this novel H1N1 infection. That is real-time RT-PCR, which basically looks at the genome, the DNA, the RNA inside of the virus, and viral culture. So what I want to highlight here from these two different methods that are currently the gold standard methods, one, this real-time RT-PCR takes several hours, but it does require substantial infrastructure in terms of running the assay. So the ability to use sophisticated equipment that runs anywhere from about $25,000 to $95,000 per instrument. So that was until recently done at the CDC for this particular novel H1N1, and it's now, those primers and that information has been shared with regional public health laboratories. So those samples are not necessarily, as I understand it, being sent to CDC anymore. The viral culture is even more intense in terms of the duration, so that takes about 2 or 3 to 10 days to complete. And what I really want to highlight here is both of these gold standard methods that are needed to establish the presence of this novel H1N1 require moderate to complex laboratory settings with highly trained operators. So that is something that could potentially be a bottleneck if we were looking at a pandemic situation. Obviously, it's not necessarily specific to this novel H1N1. So what my colleagues and I have basically identified in the engineering setting is really a critical need to translate disease diagnostics to the field and to point of care settings. So again, I'm talking about things like screening at airports, presence in developing countries, just many, many different settings that you could think of. So the problem as we see it is that current point of care technology either yields little information on novel strains or the technology, those assays, must be conducted in a centralized laboratory facility. So there's really a gap here between these fast assays, these fast measurements, and then the gold standard measurements that need to be performed. So our solution is basically, in many different ways, we're working to bring centralized laboratory capability, such as that housed at the CDC or at the public health labs, to the field. And that really motivates our engineering as related to these point of care assays. So the goal here is to quickly identify, diagnose, and manage outbreaks. And we feel that the best way to do that is to really advance technology to allow deployable detection of novel infectious diseases. So one method that several researchers here at Berkeley, and as I mentioned elsewhere, are looking at is microfluidics. And basically that method is an engineering solution that comes from the semiconductor industry. So this ability to develop complex architectures in small chips. In the semiconductor industry, we use those architectures to route electrons. In microfluidics, we use those architectures to route fluids and do manipulation of fluids. So what is the goal here? The goal is to be able to develop a fully instrumented so-called lab-on-a-chip approach. So what I talked about before. Let's take the capabilities available at the CDC and put them into a form factor that can be deployed to remote settings. We're going to try to eliminate the need for highly trained personnel. So we'd like to be able to take samples and allow an operator to put those samples into the instrument and basically hit go and then walk away and look for results coming out in some reasonable period of time. So here some of the keys are, one, we must be able to automate the entire process, and this includes the upstream sample preparation. I mentioned earlier that the assays are currently being done on respiratory samples, and those are messy samples to say the least, so we need good quality control in terms of the preparation of those samples, because the outcome of the measurements is highly dependent upon the quality of the sample going in. And then we're also looking at straightforward hardware engineering, which is how can we take these labs and put them in a form factor that's rugged and can operate in remote settings. One thing I do want to point out here is myself and colleagues have been working in this area for a decade, or over a decade in certain cases. Really, some of the recent engineering advances that are relevant to the detection of these novel infectious diseases build upon advances that have been made through personalized medicine, as well as astrobiology and space exploration, if you can believe that, which is just really interesting, and also advances that we're making in global health as well. So all of these areas and all of this engineering innovation is really intertwined. Key funding agencies that are important to this include, obviously, the National Institutes of Health, the Bill and Melinda Gates Foundation, and other foundations as well. So I just wanted to point that out. What I'm showing here on the right is a schematic that came out of The Scientist a little while ago that basically sort of embodies this concept that we're working on. Let's have a computer-operated, basically, lab on a chip. And this is a glass device right here that has what you can see are wells where fluid goes in and small channel networks that allow us to manipulate the fluids, the respiratory samples in this particular example. Okay, so what are we doing? In my last slide here, two areas that really came to mind when I was asked to present this snapshot at this meeting today. One, we're looking at how can we improve the lateral flow assays that I mentioned in the first slide. And that is we're using immunoreactions to basically identify the presence of a particular type of this influenza virus. And how can we make the sample preparation more sophisticated so that these assays are more relevant to other samples aside from just the respiratory samples, or perhaps not as dependent, as sensitively dependent upon the upstream processing that goes into collection of those samples. So we'd have a larger margin of error there, if you will, and still get a robust outcome. We're also very, very interested in looking at quantitation, and that is the ability to actually measure the amount of a particular infectious agent that's present. Right now, the lateral flow assays, if you're familiar with the home pregnancy test, similar concept, really just give you a yes-no result. What we're looking at here is being able to get more sophisticated, refined information so that we possibly could look at the spread and also the development period of the disease. And then another area I wanted to touch on just in closing is looking at microfluidics for integrated molecular diagnostics. And this is, I touched upon that real-time RT-PCR and the viral culture that are really the gold standard methods at this point, according to the CDC. Several groups are working to miniaturize and deploy methods such as that. And I've just touched upon here for forensic science, a group at Berkeley, Richard Mathis and his group are working on development of a sort of a small suitcase type instrument. Other groups are looking at integrating sample preparation that could be deployed, a very robust sample preparation. This comes from a company, Cepheid, that actually does a lot of anthrax detection for the US Postal Service, and then other groups as well. So with that, in closing, I just wanted to highlight, sort of looking to the future, I think the potential and the current impact that some of these new technologies that do seem a little bit blue sky, but can really afford us in terms of not just screening, but also monitoring and identification of these novel infectious diseases. So with that, I'll turn it back to you.
So we'll throw it open for questions. Mark?
How does the government go about making decisions in the setting of this rapidly evolving, highly uncertain set of circumstances that lead to recommendations that fan the fuels of what Wayne is calling perhaps an overreaction?
So the question is, how do government agencies make decisions and how do they try and balance appropriate concern without causing undue alarm? Is that the question? The answer is it's a very, very tricky balance to get right, to fully inform people and make sure they know what's going on without unduly alarming them. And I think that I actually have to say, I think so far the federal government and most of the agencies have done a pretty reasonable job in terms of the information they've put out there. I think the confusion is that how much of the concern is for the severity of the illness now which, as far as we can tell, is no different than the severity of annual flu, as opposed to the concern about what might happen if the virus does evolve to being more pathogenic. And I think Wayne is absolutely right that we shouldn't lose sight of the fact that in 1918, and certainly if that were to occur again today, that much of the mortality would be in poor countries. That we assume that our healthcare system would do a pretty good job of preventing mortality in rich countries. So we certainly have to take a wider view of what could happen if the virus evolves and moves, particularly into poorer settings. So I personally think they've got it more or less as good as you can get it in terms of trying to balance things, but.
I'm wondering how important you think it is for these schools to be closing down when one person comes down with the virus.
So the question has to do with school closures. I think, again, this is a tough balancing act, and I think that part of the thing you also need to take into account is the level of concern and anxiety on the part of parents and the community. So sometimes these responses in part reflect recognition that there can be great concern and anxiety, just like when there's a single case of meningococcal meningitis in a school, and many things are done because people are very, very frightened. So I think, again, it's a really tough call in an individual setting, and I don't think there's a simple yes or no answer in terms of when is that the right thing to do. Well, from a scientific point of view, there are mathematical models, and Wayne is our expert on mathematical models. There are models that suggest that school closings can reduce transmission of influenza, although they typically assume that those kids are going to be largely sequestered at home, not hanging out together at the mall. So whether kids shopping together at the mall will reduce the amount of transmission of the virus in the community, Wayne, you probably know the models better than I do, but.
Well, I'd like to answer that question without getting into too much trouble. I think it's very important to make sure that anybody who's a suspected or putative case be asked not to mix with people. This is absolutely critical. And when I talked about contact tracing, if we know of somebody who has come down with the flu, then all their schoolmates, those who've been in close contact, should be perhaps asked not to come to school, and then the school district should make some plan for making sure that they continue with their lessons. But I think that actually closing a whole school when one individual has been diagnosed with influenza is perhaps an overreaction at this particular point in time. I mean, we have to take into account the costs of doing things like closing down part of our airline industry and how many millions of dollars that may cost us per day, and how we could have spent that money better elsewhere in fighting the particular epidemic. So we certainly need to be vigilant, but we need to make sure that we're doing the right sorts of things. And it comes back to what I stress, is that it's very important to know who's been in contact with whom, and then to ask at that particular level to ask individuals, perhaps, if you have been in close contact with an individual who's just gotten it, perhaps you shouldn't go to school, but that shouldn't require us to close the whole school until it becomes obvious that there's several cases at that school, and then obviously something more drastic needs to be done.
In your reading of influenza history in the media, to what degree has the internet transformed the sort of public discourse vis-a-vis previous reportings and effects on populations or publics?
Well, I'm not sure, maybe someone else can answer that. I'm not sure I know the answer. Many of you are familiar with the recent showing by Google that they can actually detect outbreaks of influenza about 10 days before the health departments and CDC can, by simply monitoring what people are Googling. And so it's pretty clear that people do go to the web, when they get sick to seek information. And I think that's an interesting and novel approach to doing public health disease surveillance. But presumably People do get access to a lot of good information on the web, but if my children and students are any example, they sometimes get misinformation from the web as well. And I think there's a mix of good and bad information out there.
I'd like to answer that. I think certainly the internet has changed the way we do things dramatically. And if you can imagine a society where people felt compelled on Facebook to self-report that they have gotten sick so that they can let all their friends know that potentially there's a problem here, we can do the reverse process where people could let their close associates know that they have come down with the flu, and in fact, the individuals who've been in contact with them now should be more vigilant about the possibility that they could come down with it.
I think also a little bit off track here, but as an instrument designer, as a diagnostics designer, I know that we do have aspirations to use mapping capabilities like Google to help keep track of where early diagnosis or diagnosis in general is taking place. And Google.org, for example, the charitable arm of Google, is definitely very interested in that. So that's another way potentially that the web could be used.
So a few years ago, the 1918 flu strain was reconstructed, and my understanding is that it was found to be an absolutely unique virus as a virus that was in fact much more virulent in a laboratory setting than any other flu virus that has ever been detected on the planet. And so it seems to me that Wayne raised an important question that has to do with mortality rate. The mortality rate for H5N1 was, or did you say around 60% in the human population? And it seems like the cases in Mexico, from what I read in the newspaper, the mortality rate was about 10%. And that was in terms of what the reported cases were. So it seems like that was the source of some of the alarm that was raised as to the impact of this new virus on the human population, that the mortality rate seems to be higher than a typical seasonal flu outbreak. So I guess my question is, what are your thoughts as experts on the mortality rate of this swine flu, and do you think that, given that the mortality rate is probably still unknown, that the public health measures that have been instituted may or may not be appropriate?
So I would first of all caution that we don't really yet know as much as we need to about the mortality rate. It appears the number of deaths in Mexico are attributable to this virus, but I'm not quite sure that the laboratory data are there yet to support that. So I think that's going to take some sorting out. It would appear so far in other countries that the mortality is low. And again, if there are people who are not getting very sick and dying, then you obviously have to balance, how draconian the measures are you want to take to try and control something. But I think you'd have to say at the moment, and when CDC and other public health agencies began their work, that exactly how lethal this virus was, I think remained unclear and is still not entirely clear. Now, there is some molecular evidence, I believe, from CDC that this particular virus is missing some particular genetic element that's associated with high lethality. But again, these are unpublished, basically newspaper reports at the moment. So,
I would just want to add that the mortality rate is definitely one part of the equation, but it's definitely not the whole equation either, because even a virus with a relatively low mortality rate, if there's no pre-existing immunity in the population, can actually lead to a very large number of deaths. So I think there's really, potentially two reasons to be concerned about this new virus. One is that it may have a higher mortality rate than typical seasonal flu. That's not established yet. But what is pretty clear is that there's probably not that much immunity in the population to this new virus. So even if the mortality rate ends up to be same as regular flu, it could still end up being quite a lot of deaths as a result. But that remains to be seen. I mean, I think no one really knows. We're just kind of hand-waving. Yeah.
Sorry, can I just answer that? I think CDC has done a lot in the last decade to set up early surveillance systems. But as we sit out here, I'm totally unaware of what the data looks like and what the mortality rates might be. And I think a lot of the conversation that's going on in the media is done in the absence of that information. And so it may be good if the CDC had some mechanism for getting that information out earlier and telling us that maybe mortality rates are higher than a normal influenza epidemic. And if they're an order of magnitude higher, then of course we should all start instituting some kind of controls that are going to be appropriate for preparing for this kind of pandemic. But in this case, nobody said that. In fact, what I've heard the opposite, and some people from the CDC saying that it seems to be mild. But I think we need better mechanisms for getting this information out faster, and maybe we need to put those in place. Or if they are there, then they need to be better communicated to the public.
In the United States, we have regions who looks like more developing countries than the old developing countries, where population cannot access to the services and is more vulnerable, some of them for their documented conditions. So to what extent your models, being macro models, are considering this population, and what will be the advice that you would give to the public health authorities to deal with this vulnerable population?
There are a lot of people who are developing influenza models, and there's a group down at UCLA and other parts of the country, so they could better answer that. But you're definitely right. We should not be treating the United States in any way as a homogeneous area, and spatially plotting information is very, very important. I'm not sure who pointed out that, maybe Russell or somebody else pointed that out. Today we have much better technologies for tracking the spatial aspects, and we can do it district by district. And certainly I'm sure there are people who build these models who are looking at that, but we do need to take cognizance of that aspect, perhaps in the public debate that goes on, because I don't see much cognizance of that in the public forum.
But I think if the question related more to access to care and use of services, it's pretty clear that uninsured people have less access to care. People who are undocumented may be reluctant to seek care. Typically in the past we have good data that for immunizations and other things that the poor have less access to a variety of services. So I think all of those are legitimate concerns in the face of a potential epidemic that government presumably has to try and do a better job with. But let's go way in the back.
I want to understand what is causing the death. Comparing this to SARS, like my understanding was people died from SARS, but maybe with this virus, people are dying from secondary infections. So if we're better able to secondary infections.
So in terms of, first of all, there's controversy in pandemics like 1918, what killed most of the people. And if you're asking in terms of the people who've died so far in Mexico, for example, what has been the cause of death, those data are not yet published. Those cases are being investigated, but typically many of them would have secondary bacterial infections, secondary bacterial pneumonias. On occasion, there can be a primary viral pneumonia, but those would be the two primary causes of death. And what the balance is, we don't know yet.
I mean, that's actually a really good point. I can just elaborate slightly on is that in 1918, when the flu pandemic struck, we hadn't yet discovered or invented antibiotics. So and a lot of the causes of death probably were in fact probably due to secondary bacterial infections. And now, so that's probably one reason why we're better able to manage these infections now, is because we at least have antibiotics in our arsenal. Yeah, I mean, basically from an immunological point of view, SARS, I mean, I think a lot of the deaths in SARS were due to a very strong immune response, actually, on the part of the host. So sometimes the immune response can protect you, but sometimes it can also actually make you sick, which is kind of a balance that is hard to manage. And often with very newly emerged infections, the body tends to over-respond. And that can actually make you just as sick as the virus itself. So it's complicated. Lots of factors go into determining the outcome of an infection, whether you survive or die. I mean that's an interesting area for research, and that's one reason why I still think we have to do a lot of research on these kinds of infections to understand better what those factors are. Yeah.
The jump in volatility of the strains over the last 10 years, after 80 years of more or less
I mean, you're referring to that slide I showed where swine, yeah. So the swine flu was pretty stable for around 80 years, and then started to change. I mean, basically, I don't think it's not clear what the cause, why that happened exactly. I think that's always a very hard question to answer. Some people have the idea that, pig farming has changed a lot in the last, decades, and now we tend to have more pigs on fewer farms than, 50 years ago. And when you have large populations of animals in close proximity to each other, that's the kind of condition that can lead to rapid evolution of infectious diseases. But I don't think anyone's proven that that's the case. I mean, I think it would be speculation. It's certainly a very interesting question, and if we could understand that, we'd probably be a lot farther along the road to trying to preventing this thing from happening in the future as well. But I think it's still kind of mysterious, unfortunately. Yeah. I don't know if anyone wants to add to that.
I could answer that in a very general way, and that is systems can sometimes have an intrinsic stability and accumulate small changes over time, but reach a threshold where things began to change more dramatically and the system goes into a new mode. So this is just a very general answer, but it's not surprising that these kinds of nonlinear phenomena do happen.
Just to follow up a little bit, in those cases, is it a threshold and then another up and then another up, or is it? I guess what you're saying is the next threshold going to be a worse threshold than this one?
I think it's very hard to make
Yeah,
predictions about. It's like Yogi Berra says, it's hard to make predictions, especially about the future.
So the seasonal flu season usually begins with something that takes place in Asia. And so this is the first time where I can remember it really started. It seems to have started in Mexico. So do you have any speculation why this might have happened? Do you think this is also something that might continue to happen in the future, that this sort of the beginning of the flu transmission of the epidemic can shift throughout because of communities? Something to do with the pig trade or globalization of pigs?
Well, I think, first of all, there's still speculation about where the virus emerged. Did it truly emerge in Mexico? Did it emerge in Canada? Did it emerge in some other pig population and then make it to Mexico? I think no one really knows the answer to that. So what it says about the possible change in where flu viruses are going to do their evolving in the future, I have no idea.
I think one thing we do know about epidemiological processes is that the potential for an epidemic goes up greatly with population densities. And so the relative population, and also that's kind of a threshold phenomenon often. So at low densities, you usually don't have many problems. And then when you exceed a critical threshold, as you go above that, you begin to have issues and problems. And in this case, it's not only a threshold in the human population, but also in densities of agronomic systems, pig farming, and so on. So I think that's a good question. Maybe there's a much higher level of pig farming now in Mexico than there may have been 1 or 2 decades ago, and this could signal a shift.
'57. Have they discovered anything that makes it possible to determine if they're going to succeed if another epidemic comes, or flu or pneumonia, or does it depend on the age, like over 60? Or they didn't cover those ages, by the way.
So the answer to your question, if your question is, if people have had prior exposure to various influenza viruses in '57 or '68, or even had the swine flu vaccine in 1976, are they protected against this virus? The answer is we don't know. There's no reason to think that having had flu before with any of the strains we know of would offer you protection against this virus. People are currently trying to figure out whether having gotten the swine flu vaccine in '76 is going to offer any protection to those 40 million people, but we don't know the answer to that yet either.
So to be on the safe side, if you're in proximity with a lot of people who travel to Mexico, they live in the area where you live, you just kind of take care of yourself. You don't be around them, I guess, because it's the only, there's no known anything to take care of it. Is that right?
Well, there are pretty good ways for treating people, but fortunately most people with influenza recover on their own. You know, that's the reality. Is it's a very small proportion of people with flu who need hospitalization or who need specific treatments at the moment.
It's the people that have had more things wrong with them, I guess. They need to have.
So maybe I'd be happy to answer you. Let me just
Thank
see
you.
if there are any other questions before we wrap up, and then I'll be happy to, yeah.
Yeah, it's a interesting question. I don't know if you've ever heard it, but the question is this triple reassortment virus that's been circulating in swine for some time. What about it that has essentially allowed it to jump back into humans? I think that's going to be an active area of investigation, but we have no idea. It's probably a little bit simplistic to say that it's the human segments that allow it to replicate in humans. It's probably not that simple. It's some combination of probably multiple factors that have allowed it to make that jump back into humans. I think it's a very interesting biological question, but I think it's very far from being understood completely. So I'm sorry I can't really give you much more of an answer than that.
Okay, we'll take a couple more questions, then we're gonna have to wrap up at 3. Yeah.
So my roommate went to Mexico over spring break, right? Puerto Vallarta, had some bad chili rain, a little bit of indigestion associated with that. But he comes back, and a month later he gets really sick from the flu, right? And right as this whole thing's sparking up, so we're all cracking jokes about it, and we think it's kind of funny. But he keeps getting worse and worse, so he goes down to the Tang Center, which is like the student health center. And they really don't do anything, They run a blood test and they tell him he's got the flu, but my question is when are they going to be actually doing PCR and sequencing all these pathogens in U.S. hospitals? Because I think, it sounds like what's holding us back is the cost of the instruments, but this is what we got to be doing,
Good,
right?
Amy can
Who knows
handle
what he's got?
Yeah, I think that's an absolutely great question. I think that's sort of the vision that I was trying to share today. And there are absolutely, in centralized lab facilities, you do real-time RT-PCR, or in other facilities, viral culture. If you have a certification, a biosafety level 2 certification, for example, you can do that. I think what we're looking at is just looking into the future, as you said, I think in the next 5-10 years, you're definitely going to start to see, even before 5 years, you're definitely going to start to see more sophisticated assays being done in a distributed format. And I think a lot of it is actually being driven by our interest in global health, by people looking at distributing this to, resource poor settings, basically. So in my mind, I think in the next 3 years, we're definitely going to see a surge in new assays that are being done, probably multiplexed assays for looking at multiple analytes. It's something that's a little bit difficult to do now at the point of care. But most certainly within the next 5 or 10 years, start to see a lot of these much more sophisticated assays being done. Yeah.
But just to put that in context, clinicians order tests when tests are helpful in taking care of patients. And not all tests are helpful in taking care of patients, even if they're helpful to people in public health for epidemiologists. So that's the other issue, whether the test actually has clinical utility.
Am I on? Yeah. I may be a little bit controversial here, but what I want to do is propose 4 new ways of coping with the flu, which you haven't really mentioned yet. First is to prevent a new and virulent form of flu from coming into existence. Let everyone on Earth know that when you are sick with the flu, avoid people and totally avoid sick birds and sick pigs, because it's in the sick birds and the sick pigs and the sick people when they all mix. Everybody should know that. Maybe these people here hearing that will have known that, but it hasn't been made public knowledge, and you people are in a position to do that, I think. Another thing, I would say to the person on the right, take your hand away from your face. We should teach people around the world now that when they sneeze, they should sneeze into their left elbow, and when they have to scratch their nose, they scratch it with their right elbow. That's a simple thing. The person in the depths of Africa that have no access to Tamiflu or Cepheid, Bystock and Cepheid, or any of these other things, or Relenza, they don't have access to those. They don't have access to a vaccination. They don't have access to high-tech medical things. But they do have access to not transmitting the flu to their friends by coughing into their left side and wiping their nose to the right side. So that's two of them. The third one is, and this is going to get really weird and people are going to hate it.
Okay, we're going to have to wrap up in a minute, so try and keep it brief. Okay?
I'm actually trying to cure the flu rather than talking about how uncurable it is. So anyway, the third point I would like to make is there was a thing that came about before vaccination called viralization, where you took a smallpox vaccine from underneath of somebody who was recovering from smallpox and scratched yourself with it. That way you only had a 1% death rate instead of a 30% death rate. We can do the same thing if you're in the depths of Africa with the flu. If you catch a severe flu and you take, somebody catches it in your community, and you take some of the mucus, the snot, from their nose and put it in your own nose, you're going to catch the flu. But it's not going to be in your lungs and in your throat, which is where you will catch the flu if you catch it from a cough.
I'm sorry to interrupt. I just wanted to let everybody know that it's 3 o'clock and there is a class coming in now. I'm sorry to cut it short.
Okay, thank you.
Thank you all very much.